Most of our universe is made of something we cannot see. Dark matter is the invisible cosmic architect, shaping every galaxy and star while remaining completely hidden from our eyes. You will understand how scientists map this ghostly substance and why it dictates the ultimate fate of the cosmos. How did we first discover the presence of this missing mass, and what strange particle could it be made of? What does this hidden world tell you about the nature of reality itself? Galaxies should tear themselves apart. The stars at their outer edges whirl around the center at such tremendous speeds that the gravity from all the glowing stars and gas we can see is nowhere near strong enough to hold them in place. Yet these vast cosmic islands remain perfectly intact. This glaring contradiction was thrust into the scientific spotlight by the meticulous work of astronomer Vera Rubin. She was not looking for a revolution, only answers, as she measured how fast stars orbit within spiral galaxies. The data revealed something astounding. Stars far from the galactic core were moving just as fast as those near the center. This defied all expectations. According to the established laws of gravity, these outer stars should have been moving much more slowly, like planets in our own solar system where distant Pluto crawls compared to Mercury's rapid sprint. The only possible explanation was that something else was there, something invisible, adding a tremendous amount of gravity. This missing mass created a gravitational anchor, a hidden force strong enough to keep these high-speed stars from flying off into the void. The evidence was no longer just a theoretical curiosity. It was a physical reality etched into the motion of every galaxy. How could our maps of the cosmos be so incomplete? This fundamental question forced a profound shift, compelling scientists to propose the existence of a mysterious substance that neither emits nor absorbs light, a ghostly presence we now call dark matter. The evidence was etched in light, a silent story told by the motion of stars. To truly grasp this cosmic mystery, you have to look at a specific kind of map, a graph astronomers call a rotation curve. It plots a simple but profound relationship, the orbital speed of stars against their distance from the galactic center. Picture our own solar system for a moment. The planets closer to the Sun, like Mercury, whip around at incredible speeds, while the outer worlds, like Neptune, move in a slow, stately crawl. This is exactly what the laws of gravity predict when the mass is concentrated in the center. For decades, scientists assumed galaxies would behave the same way. The bright core, packed with billions of stars, should act as the central anchor, with stars slowing down the farther out you go. But when Vera Rubin and others finally measured these speeds, the graph they produced sent a shockwave through astronomy. The rotation curve was not a steeply falling line. It was flat. Stars at the very edge of a galaxy were hurtling around just as fast as those near the bright interior. It was as if every single car on a vast, sprawling highway, from the downtown on-ramps to the most distant rural exits, was traveling at an identical, breakneck speed. This was not just unexpected, it was physically impossible according to everything we thought we knew. The gravity from all the stars and gas we could see was utterly insufficient to hold these speedy outer stars in their orbits. The only logical conclusion was that galaxies are not just what we see. They are embedded within a gigantic, invisible sphere of matter, a halo that extends far beyond the luminous disk. This dark matter provides the extra gravitational glue, the unseen hand that keeps entire galaxies from spinning themselves apart. The flat rotation curve was not a minor anomaly. It was a fundamental flaw in our inventory of the cosmos. The hunt for the invisible substance causing this effect was now officially on. But the ghost left more than one fingerprint. across the vast emptiness of space, light itself is being tricked. A distant galaxy does not appear as a single, sharp pinprick. Instead, it is stretched into a faint, shimmering arc, a cosmic mirage. This bizarre effect is called gravitational lensing, and it is dark matter's most dramatic calling card. The phenomenon was predicted by Albert Einstein's theory of general relativity, which revealed that mass warps the very fabric of space and time. Think of spacetime as a taut, rubber sheet. Place a heavy bowling ball in the center, and it creates a deep dimple. Now roll a marble past the bowling ball. The marble will not travel in a straight line, it will curve along the indentation. In the cosmos, the bowling ball is a massive object like a galaxy cluster, and the marble is a beam of light traveling from a distant star. The gravity of the cluster bends the light's path, acting as a giant natural lens. This lens does not just bend the light, it can distort and magnify the image of the background galaxy, twisting it into those strange arcs and sometimes even creating multiple copies of the same object in the sky. Here is the crucial part for our hunt. When astronomers calculate how much mass the galaxy cluster must have to create such a powerful lensing effect, they run into the same problem Vera Rubin did. The visible stars and gas account for only a tiny fraction of the needed gravity. The rest, the overwhelming majority of the mass bending the light, is completely invisible. This allows scientists to perform a kind of cosmic cartography. By meticulously analyzing these distorted images, they can map where the gravity is strongest and therefore where the dark matter is hiding. The result is not just a confirmation of its existence, it is a detailed blueprint. These maps reveal that dark matter is not smoothly spread out. It forms an intricate, colossal web, a scaffolding upon which the luminous galaxies are merely strung like dewdrops on a spider's silk. Through the warped light of distant suns, we are finally drawing the first true maps of our invisible universe. The final piece of evidence comes from the dawn of time itself. Billions of years ago, the entire cosmos was a seething, hot plasma, a dense soup of particles and light. As the universe expanded and cooled, light was finally set free, creating a flash that still echoes throughout all of space. Today, we detect this as a faint, cold glow, a relic radiation known as the cosmic microwave background. It is the oldest light we can see, a baby picture of the universe. Satellites like the Planck mission have mapped this afterglow with incredible precision, revealing it is not perfectly uniform. The map is flecked with tiny variations, minuscule hot and cold spots that represent the seeds of all future structure. These tiny ripples are the gravitational blueprints for everything to come, the first over dense regions that would eventually pull in matter to form galaxies and clusters. But the patterns in this primordial light tell a very specific story. The size and distribution of these spots reveal the total amount of matter in the early universe and how it behaved. The data shows that ordinary matter, the atoms that make up stars and planets, was constantly buffeted by the intense radiation pressure in that early hot soup. This pressure prevented it from clumping together effectively. For the universe we see today to have formed, with its vast web of galaxies, there had to be another type of matter present. This substance had to be immune to light's push, a form of matter that could start gathering into gravitational wells long before atoms could. The cosmic microwave background provides the definitive proof that this matter exists. The patterns we observe only make sense if a large portion of the early universe was made of something cold and dark, a substance that could gravitationally collapse without being pushed apart by radiation. This snapshot from the universe's infancy confirms that dark matter is not a minor component. It was a primary ingredient from the very beginning, the invisible framework upon which the visible cosmos was built. So what exactly is this invisible cosmic architect made of? The search for an answer begins not with what it is, but with what it cannot be. It is not, for instance, the same stuff that makes up you, me, or the stars. That familiar matter, built from protons and neutrons, is what scientists call baryonic matter. We have meticulously weighed the universe and found a startling imbalance. The total amount of ordinary baryonic matter is only about 1/6 of the total mass required to create the gravitational effects we observe. Dark matter is something else entirely, a substance that does not interact with light in any way. It is not simply a cloud of cold hydrogen gas or a swarm of rogue planets, as these would still block or emit some form of radiation that our telescopes could detect. It is also not antimatter. When a particle of matter meets its antimatter counterpart, they annihilate each other in a brilliant flash of energy. If dark matter were antimatter, we would see the sky ablaze with the constant fireworks of these annihilations, a glow that is conspicuously absent from our observations. For a time, some scientists wondered if dark matter could be hidden in the form of black holes, specifically primordial black holes forged in the universe's first chaotic moments. But detailed studies have largely ruled this out. The way light from distant stars subtly flickers as it travels to us shows that such compact, dark objects are far too rare to account for the immense gravitational pull we measure. So we are left with a profound emptiness. Dark matter is not any known form of atomic matter. It does not absorb light, it does not emit it, and it does not reflect it. This process of elimination, while narrowing our options, is actually our greatest guide. It pushes us toward the frontiers of theoretical physics, to the possibility of an entirely new class of particle that has so far eluded our most powerful detectors. This ghostly substance is not just hidden matter, it is a different kind of reality altogether. The most promising answer to this cosmic riddle is a phantom known as a WIMP. This stands for Weakly Interacting Massive Particle, and its name perfectly describes its elusive nature. Imagine a particle that has mass, so it exerts a powerful gravitational pull, but it is completely blind to light and mostly ignores normal matter. It would only interact through gravity and the weak nuclear force, the same fundamental force responsible for radioactive decay. This profound aloofness is precisely why it has remained hidden for so long, passing through our planet and even our bodies by the trillions every second without a trace. What makes this idea so compelling to physicists is a concept known as the WIMP miracle. It is a remarkable piece of cosmic serendipity. The mathematics of the early universe show that if a stable particle with exactly these properties, massive and weakly interacting, existed, it would have been forged in the Big Bang's aftermath in precisely the right amount to explain the dark matter we observe today. The numbers align so perfectly that it feels less like a guess and more like a prediction from the universe itself. To catch one of these phantoms, scientists have built some of the most sensitive detectors on Earth, housed deep within mountains or in abandoned mines. These laboratories are buried under thousands of feet of rock to shield them from the constant rain of cosmic rays that would otherwise drown out the signal. Inside, they wait for an event of incredible rarity, the minute recoil of a single atomic nucleus as a WIMP, after its long journey across the cosmos, finally bumps into it. This search for an almost imperceptible tremor in the dark is one of the most ambitious and patient experiments in human history, a direct hunt for the invisible architect of our universe. But WIMP are not the only phantoms in the running. Another compelling candidate emerges from the deepest puzzles of quantum physics, a hypothetical particle called the Axion. Originally, axions were not invented to explain dark matter at all. they were proposed to solve a nagging mystery in the theory of the strong nuclear force, the glue that holds the cores of atoms together. The math of this force seemed to allow for a strange asymmetry that should make neutrons behave differently in electric fields, an effect no experiment has ever observed. The Axion was a clever theoretical fix, a new particle whose existence would neatly restore this cosmic balance. Yet physicists soon realized this humble problem solver had a secret superpower. If axions do exist, they would be born in staggering numbers during the Big Bang. They are conceived not as heavy particles, but as incredibly light ones, potentially billions of times lighter than an electron. Their immense population, however, could make up for their tiny individual mass, flooding the cosmos in a coherent, wave-like field. Picture an ocean so vast and so fine that its individual droplets are imperceptible, yet its collective current is powerful enough to shape entire continents. This is the Axion field, a subtle, rippling energy that permeates all of space. Its gentle gravitational pull could very well be the dark matter we have been searching for. This possibility has launched a completely different kind of hunt. Instead of waiting for a rare collision in a deep underground vault, scientists are now building intricate experiments to coax axions into revealing themselves. The method relies on their potential to transform. In the presence of an immensely powerful magnetic field, an axion might spontaneously convert into a faint microwave photon, a single particle of light. These experiments are essentially giant, ultra-sensitive radio receivers, tuned to listen for the faint whisper of dark matter turning into light inside a magnetic chamber. It is a search for a ghostly chime in a silent room, a testament to the incredible creativity required to map the invisible. The existence of such different candidates, from heavy WIMP to wave-like axions, shows just how wide open this frontier remains. We are not just testing one idea, we are exploring the entire spectrum of what might be, probing the shadows with every tool our ingenuity can devise. To bridge the gap between theory and observation, scientists have constructed entire universes inside supercomputers. These are not simple animations, they are profound digital experiments known as N-body simulations. The N stands for the number of particles, a number that can soar into the billions, with each single particle representing a vast cloud of dark matter. The rules of the simulation are deceptively simple, governed only by gravity. The computer calculates the gravitational pull between every single one of these billions of particles as they move through an expanding virtual space. It is a cosmic dance of unimaginable complexity, choreographed by the most fundamental force in the universe. One of the most famous of these digital creations is the Millennium Run. In this simulation, researchers watched over 10 billion particles of dark matter, tracing their evolution across more than 13 billion years of cosmic history. The results are breathtaking. From a nearly smooth starting point, the dark matter does not just clump randomly. It collapses under its own immense gravity, weaving itself into an intricate, three-dimensional tapestry. This is the cosmic web in its full glory, a network of vast, empty voids bordered by thick filaments of dark matter, all connecting at dense nodes called halos. This is the invisible skeleton of our cosmos, and it is within the deepest gravitational wells of these dark matter halos that the story of our own galaxy begins. Ordinary gas, drawn in by the halo's immense pull, cools, condenses, and finally ignites into the first stars. Every galaxy we see, including our Milky Way, is perched at the heart of one of these invisible dark matter anchors. The true power of these simulations lies in their predictive ability. By comparing this simulated cosmic web to the actual distribution of galaxies mapped by our most powerful telescopes, we can run a test. Does the virtual universe built on our assumptions about dark matter grow to look like the real one? So far, the match is strikingly good, confirming that our basic understanding of this ghostly architecture is correct. These digital universes are more than just movies. They are fundamental laboratories, allowing us to watch cosmic evolution unfold over billions of years in a matter of weeks. These digital laboratories are now evolving into something even more profound. The Illustris TNG project represents a monumental leap beyond pure dark matter simulations. Here, the universe is not built from gravity alone. The code breathes life into a virtual cosmos by weaving together the complex physics of ordinary matter. Supercomputers now model the violent birth of stars within collapsing gas clouds, the searing energy of supernova explosions, and the ferocious appetite of supermassive black holes lurking in galactic cores. This is a universe in high fidelity. When the simulation runs, it does not just produce a web of dark matter, it populates that web with realistic galaxies. Spirals with graceful arms, ellipticals like giant orbs of aging stars, and dwarfs scattered like cosmic seeds all emerge from the calculation. Their sizes, shapes, and distributions match the patterns our telescopes observe with stunning accuracy. This realism is the key to unlocking dark matter's ultimate role. The simulation reveals a constant cosmic dialogue. Dark matter's invisible scaffolding provides the gravitational wells where gas can pool and cool. This gas then forms stars whose eventual deaths in supernova blast energy back out into space, heating the surrounding gas and preventing new stars from forming too quickly. At an even grander scale, the supermassive black holes at the center of galaxies join the conversation. As they devour matter, they unleash titanic jets of radiation and wind, powerful enough to blow gas clear out of a galaxy, effectively shutting down star formation for eons. This process, called feedback, is what gives galaxies their final form. Without the regulating influence of stars and black holes, galaxies would grow too massive, too bright, and look nothing like the ones we see. The dark matter halo sets the stage, but this feedback choreographs the dance of light. These virtual universes have become an indispensable tool for interpreting the faint signals from our most powerful observatories. When astronomers point a telescope at a distant galaxy cluster, they see a single, frozen moment in its multi-billion-year life. A simulation like Illustris TNG allows them to rewind and fast-forward to understand the dynamic processes that led to that exact arrangement of stars and gas. It answers questions we could never ask otherwise. Why does one galaxy remain a vibrant star-forming factory while its neighbor becomes a quiet, red, and dead relic? The answer is written in the intricate balance between the pull of the dark and the push of the light. There is another, more subtle way to see the invisible. Across the vast cosmic ocean, the shapes of distant galaxies are being imperceptibly stretched. This is the world of weak gravitational lensing, where the distortions are too faint to see with the naked eye, but reveal everything when viewed in aggregate. Instead of the dramatic arcs and rings of strong lensing, weak lensing produces only a tiny, systematic alignment. Imagine looking through an old, slightly warped windowpane at a field of distant flowers. No single blossom appears dramatically distorted, but if you were to measure millions of them, you would find that they are all very slightly stretched in the same direction, aligned by the invisible imperfections in the glass. Astronomers perform this same statistical miracle on a cosmic scale. They painstakingly measure the precise shapes of millions upon millions of faint background galaxies. The gravitational influence of the dark matter web between us and those galaxies acts as that warped pane, coaxing the galaxy's shapes into a faint, coherent pattern. This collective distortion is known as cosmic shear. It is an almost impossibly delicate signal buried in a sea of random orientations, but by applying immense statistical power, it can be extracted. This data is the raw material for the most detailed maps of the cosmic web we have ever created. By analyzing how the shear changes with distance, astronomers can perform a kind of three-dimensional tomography, charting the dark matter structures not just as a flat picture, but in depth, revealing their true colossal architecture. This technique turns the entire observable sky into a single, gigantic dark matter detector. It allows cosmologists to do more than just find the missing mass. They can literally weigh immense galaxy clusters by measuring how their dark matter halos warp the space around them. Even more profoundly, by mapping the cosmic web at different epochs in the universe's history, they can trace how the strength of the dark matter's gravitational pull has influenced the rate of cosmic expansion over billions of years. In the subtle, stretched shapes of countless galaxies, we find the signature of the invisible universe, a ghostly fingerprint pressed into the light of everything we see. This immense statistical power was harnessed by one of the most ambitious sky surveys ever conducted. The Dark Energy Survey spent 6 years peering deep into the southern sky from a mountaintop in Chile, using a camera of almost unimaginable resolution. Its 570 megapixel eye collected light from hundreds of millions of galaxies, each one a tiny data point in a cosmic census of staggering scale. The primary mission was to stare directly into the heart of darkness, not just dark matter, but its even more mysterious counterpart, dark energy. To do this, it relied heavily on the subtle signal of weak gravitational lensing. The team measured the shapes of over 100 million galaxies, searching for that faint, coherent warp imposed by the invisible cosmic web. The result was the largest map of dark matter distribution ever created, a chart of the unseen that covers 1/8 of the entire sky. This map is more than just a picture, it is a precision scale for the cosmos. The data from the survey allowed scientists to measure the total amount of clumpy dark matter and the smooth, repulsive force of dark energy with a razor's edge accuracy never before achieved. These measurements act like a key, tightening the constraints on our fundamental models of the universe. They tell us, with less room for error than ever, how much of each mysterious component exists and how they have shaped cosmic evolution. This was not the work of a lone astronomer, but a massive collaboration of hundreds of scientists across the globe. It represents a new era of astronomy, where answering the universe's biggest questions requires a symphony of effort, blending cutting-edge engineering, vast computational power, and relentless analytical curiosity. The terabytes of data collected are a gift that keeps on giving, a treasure trove mined not just for dark matter, but for discoveries about our own solar system, the life cycles of stars, and the nature of the most distant galaxies. The faintest threads of the cosmic web have finally been photographed. For years, the grand architecture predicted by supercomputer simulations remained just that, a prediction. We could see the dense clusters of galaxies, the glittering nodes where the dark matter filaments met, but the connecting threads themselves were too ethereal, too diffuse to see directly. That changed with a painstaking campaign using the Hubble Space Telescope. Astronomers targeted massive galaxy clusters, but they were not looking at the clusters themselves. Instead, they trained Hubble's exquisite vision on the light of even more distant quasars, the brilliant cores of active galaxies. Their strategy was one of supreme subtlety. They reasoned that even a wispy, billion-light-year-long filament of dark matter would possess enough gravity to act as a minuscule lens. It would not create dramatic arcs, but it would impose a tiny, specific distortion on the quasar's light, a barely perceptible shear. The challenge was that any single filament's effect was vanishingly small, lost in the noise. The solution was statistical power. By combining Hubble's observations of different quasars seen through the predicted paths of different filaments, they could amplify the faint signal. It was like listening for a whisper in a crowded room by combining the ears of thousands of listeners, each one confirming a single, soft syllable. The result was a landmark achievement, the first direct detection and measurement of these elusive tendrils. By analyzing the precise warping of the quasar light, the team could effectively weigh the filament. They confirmed it was indeed made of dark matter and that it contained a staggering amount of mass, enough to bind entire clusters together across the void. This was not just more evidence for dark matter, it was a direct observation of the cosmic skeleton itself. The cold dark matter model had long said the universe should look this way, a web of dark matter with galaxies strung along it like dew on a spider's silk. Now we had a picture of the silk. This confirmation from the deepest reaches of space told us we are not just guessing at the shape of the cosmos, we are finally reading its blueprints. These colossal galaxy clusters are the ultimate testing grounds for the invisible. Within their immense gravity, dark matter reveals itself not through one clue, but through a chorus of evidence. A single massive cluster acts like a multifaceted cosmic laboratory, where astronomers can conduct multiple experiments at once. First, they observe the intense gravitational lensing, the dramatic warping of background galaxies that maps the cluster's total mass. Then, they measure the velocities of individual galaxies orbiting within the cluster, their high speeds betraying the powerful gravitational field holding them in place. Finally, they point X-ray telescopes at the cluster, revealing a seething cloud of superheated gas. This gas, trapped by gravity, glows brightly, and its distribution and temperature allows scientists to calculate how much mass from ordinary matter is present. When these three independent measurements are compared, a consistent and startling picture emerges. The gravity required to explain the lensing and the galaxy motions is always far greater than the gravity from the hot gas and the stars we can see. This triple confirmation leaves no doubt that a vast sphere of dark matter dominates the cluster's core. But the most stunning evidence comes from cosmic car crashes, the violent collisions of entire galaxy clusters. The Bullet Cluster provides perhaps the most famous and visually compelling case. This system is actually two clusters that have smashed right through each other. During such a collision, the different components behave in extraordinary ways. The clouds of hot, X-ray emitting gas from each cluster, made of ordinary matter, slam together. They experience a drag force like two clouds of smoke colliding and slow down, lagging in the center of the wreck. The galaxies themselves, mostly empty space, pass by each other largely unaffected. And the dark matter, which does not interact with itself or the gas, simply coasts right through the chaos. So, how do you map the aftermath? Scientists combined observations. The Chandra X-ray Observatory pinpointed the location of the ordinary matter, the stalled gas, glowing brightly in the middle. Then, by using weak gravitational lensing to map where the majority of the mass ended up, they found the true gravitational anchors of the system. Two distinct clumps of mass were clearly visible, each having sailed far ahead of the gas. The dark matter had become physically separated from the normal matter. This was not an indirect inference, it was a direct image of dark matter's ghostly nature. It demonstrated conclusively that most of the mass in the universe is made of something that neither emits light nor interacts with the familiar atoms we are made of. These cosmic collisions offer a pure, untainted view of the invisible universe, a portrait of dark matter standing apart from everything else, deep underground, in the profound silence of abandoned mines and mountain caverns. some of the most patient experiments in human history are waiting for a ghost to bump into a wall. These are the direct detection experiments, and their task is almost impossibly difficult. They are not looking out at the cosmos, but inward, into vats of the purest material on Earth, hoping to catch the one in a trillion interaction that confirms a dark matter particle's existence. Laboratories like LIXZEPLIN and XENONNT are marvels of engineering buried under thousands of feet of solid rock. This immense natural shield is absolutely essential. It blocks the constant, chattering rain of cosmic rays from space, particles that would create a deafening background noise and completely drown out the whisper-quiet signal they are designed to hear. At the heart of these detectors are massive tanks filled with liquid xenon, chilled to extreme temperatures. Xenon is chosen for its dense atomic nucleus, offering a larger target for a potential collision. The entire setup operates in total darkness, colder and quieter than the void between stars. The theory is simple in principle, yet staggering in its sensitivity. If a WIMP, a weakly interacting massive particle, is truly flooding through our world, then at any moment one might, by sheer chance, strike the nucleus of a xenon atom. This collision would be incredibly gentle, but it would produce two telltale signs: a tiny flash of scintillation light and a puff of electrical charge. An array of ultra-sensitive sensors called photomultiplier tubes lines the tank, waiting to capture that single, fleeting photon of light and the corresponding electron signal. It is the scientific equivalent of listening for the sound of a single pin dropping in a silent city. The silence, however, is what speaks volumes. Despite these detectors reaching levels of sensitivity that were once pure science fiction, no definitive, unambiguous signal has ever been recorded. The flash of light has not come. This persistent null result is not a failure, it is a fundamental piece of the puzzle. Every time an experiment like this comes up empty, it carves away another chunk of possibility from our theoretical models. It tells us that dark matter, if it is a WIMP, must be even more aloof or have a different mass than we had hoped. We are not just searching for a particle, we are meticulously mapping the edges of its absence, drawing the silhouette of the invisible by where it decidedly is not. While underground labs listen for a whisper, other scientists are searching for a ghost shadow. This alternative strategy is known as indirect detection, and it does not look for the dark matter particle itself. Instead, it hunts for the radiant aftermath of its destruction. The theory rests on a fascinating possibility. What if a dark matter particle is its own antimatter counterpart? If this is true, then whenever two of these particles collide, they would annihilate each other in a silent, invisible flash of pure energy. This energy would then reconstitute itself into a shower of secondary particles we can detect, such as gamma rays, the most energetic form of light, or a spray of neutrinos and antimatter particles like positrons. Think of it not as seeing the ghost, but as finding its glowing footprints left in the cosmic sand. To conduct this search, astronomers use some of the most powerful eyes in space. The Fermi Gamma Ray Space Telescope, with its large area telescope instrument, constantly scans the entire sky. It is not looking at stars or galaxies, but at the high-energy gamma-ray light that paints the cosmos. The mission is to find an anomalous glow, an excess of gamma rays that cannot be explained by any known astrophysical process, like a pulsar or a black hole jet. The most promising places to look are regions where dark matter is thought to pile up in immense densities. The very center of our own Milky Way galaxy is one such cauldron, a gravitational well so deep that dark matter should be swarming. Another prime target is a class of faint, tiny galaxies that orbit our own, called dwarf spheroidals. These are ancient, dim collections of stars that are so dominated by dark matter, they are essentially floating bags of the stuff with a few stars mixed in. They are perfect, pristine laboratories because they have very few of the conventional astrophysical sources that could create confusing gamma-ray signals. Finding a sharp, unexplained spike of gamma rays emanating from the heart of a dwarf galaxy would send a shockwave through the world of physics. It would be the signature of a fundamental process, the self-annihilation of the universe's most elusive substance. This is the promise of indirect detection. It turns the entire sky into a canvas, and on it we are looking for the faint, telltale brushstrokes left by an invisible artist. For more than 20 years, a single experiment has reported a ghostly heartbeat. Deep within the Gran Sasso mountain in Italy, the DAMA Libra experiment has detected a signal that rises and falls with the seasons. The researchers are not observing flashes of light in a xenon tank, but a subtle, rhythmic change in the rate of tiny flashes in a crystal detector. This annual modulation is the heart of their claim. They argue it is the signature of our entire solar system sailing through the Milky Way's river of dark matter. As Earth orbits the Sun, our planet's velocity adds to or subtracts from the solar system's overall speed through this galactic halo. In June, we are moving headfirst into the stream, and in December, we are catching up to it from behind. This change in our relative speed should cause the number of dark matter particles hitting the detector to peak in the summer and ebb in the winter. The data from DAMA Libra shows this exact pattern, a sinusoidal wave that has repeated like clockwork for over 20 cycles. It is a compelling story, a perfect match between prediction and observation. Yet this signal stands completely alone, a solitary voice in a crowded field. No other major dark matter experiment has been able to reproduce this result. The controversy this creates is not one of rivalry, but of fundamental scientific process. How can one experiment see a clear signal for decades while others, often using similar or even more sensitive technology, see nothing at all? The scientific method demands independent verification. A result must be repeatable to be accepted as a discovery. The stubborn isolation of the DAMA signal has forced physicists to dig deeper, to look for any possible explanation other than dark matter. Could it be an unknown seasonal effect? A subtle interplay of cosmic rays with the atmosphere that changes throughout the year, or perhaps a fluctuation in the detector's own background noise that coincidentally mimics the expected modulation. Dozens of alternative experiments have been designed specifically to test the DAMA claim, using different materials and techniques to rule out these systematic errors. So far, they have all returned empty-handed. This enduring mystery highlights a critical crossroads in the hunt. Either DAMA Libra has discovered dark matter using a method others cannot replicate, or it has uncovered a complex, unknown background effect that perfectly mimics a dark matter signature. Both possibilities are profound. Resolving this puzzle is now a primary goal for the next generation of detectors, which will use the same crystal materials as DAMA in an attempt to finally confirm or refute this tantalizing, persistent rhythm. The answer will either be a triumphant validation or a humbling lesson in the immense challenges of seeing the invisible. Perhaps our entire approach has been a grand illusion. What if the ghost we have been chasing for decades is not a particle at all, but a phantom created by a fundamental flaw in our understanding of gravity itself? This is the radical proposition of modified Newtonian dynamics, or MND. It was first introduced by physicist Mordechai Milgram, who dared to ask a heretical question. Instead of inventing a new, invisible substance to explain galaxy rotation curves, what if we are just using the wrong rulebook, Newton's laws, and even Einstein's refinements, work flawlessly in our solar system and in most laboratory tests. Buttman proposes that on the immense, diffuse scales of galaxies, where gravitational fields become almost impossibly faint, the rules change. There is a new, subtle acceleration scale that kicks in. Below this threshold, gravity stops weakening with the square of the distance and instead follows a different, gentler decline. This single adjustment makes the math work. The flat rotation curves of galaxies, the very same data that convinced us of dark matter, emerge perfectly from Mund equations without a single invisible particle. It is an elegant solution, a way to fix the cosmic books not by adding missing entries, but by correcting a calculation error we never knew we were making. For its supporters, this is not just a theory, it is a philosophical stance. It insists that we should exhaust all possibilities within the known laws of physics before conjuring up an entirely new, undetectable universe. And for individual galaxies, Mund works remarkably well. It predicts the motions of stars with a precision that often matches or even exceeds the dark matter model. But elegance on a small scale can shatter when faced with the universe's grandest experiments. The theory stumbles when confronted with the bullet cluster. Remember the cosmic collision where the dark matter sailed cleanly through, separating from the visible gas. Mund, in its original form, has no invisible mass to separate. The gravitational lensing map that shows mass where there is no light becomes an inexplicable paradox. It also struggles to account for the detailed patterns in the cosmic microwave background, the universe's baby picture. The specific sizes of the hot and cold spots are a perfect imprint of a cosmos dominated by cold, clumpy dark matter from the very beginning. To make Mund fit this evidence, its proponents have had to introduce new fields or even a tiny amount of hot dark matter, tweaks that to its critics begin to look suspiciously like the very invisible substance the theory was designed to avoid. This is the heart of a theoretical battle that divides cosmology. Are we missing most of the matter in the universe, or are we missing a crucial chapter in the laws of physics? The choice is not merely technical, it is foundational. Do we trust our equations so completely that we are willing to populate the cosmos with phantoms to make them balance? Or do we take the universe's strange behavior as a direct challenge to our most cherished theories? This conflict forces a profound and necessary humility, reminding us that every great mystery is also a mirror, reflecting the limits of our own perception. The ultimate destiny of the cosmos is written in the language of gravity, a cosmic tug of war between two invisible giants. On one side, you have the relentless push of dark energy, driving the universe to expand at an accelerating rate. On the other, you have the patient, persistent pull of dark matter, the gravitational anchor trying to hold everything together. The balance between these two forces will decide the final fate of all that exists. The critical factor is the total density of the universe, the amount of stuff, both seen and unseen, contained within the cosmic volume. Dark matter makes up the vast majority of this gravitating mass, and its precise quantity acts as a cosmic brake on the expansion. Think of it like throwing a ball straight up into the air. If the ball has enough mass, Earth's gravity will eventually stop its ascent and pull it back down. The universe operates on the same principle. If the combined density of dark matter and normal matter is high enough, its collective gravity will eventually overcome the expansion, reversing it in a cataclysmic event cosmologists call the Big Crunch. The entire universe would collapse back in on itself, a fiery and spectacular end to space and time. For a long time, this was considered a very real possibility. Yet our most precise measurements, from the cosmic microwave background to the mapping of distant supernova, point toward a different, and in some ways more lonely, future. The data reveals that while there is a tremendous amount of dark matter, its gravitational pull is not strong enough. The density of the universe falls short of the critical value needed to halt the expansion. The brake is powerful, but the accelerator is stronger. This leads us to the prevailing forecast for our cosmic destiny, a future known as the Big Freeze. In this scenario, the expansion driven by dark energy continues unchecked. Over trillions of years, galaxies will recede from one another until they are isolated islands in an ever-darkening void. Star formation will cease as gas reservoirs are depleted, and one by one the stars will burn out. The universe will grow cold, dark, and dilute, approaching absolute zero. The presence of dark matter, in a final, profound irony, is the very reason this eternal expansion is our likely fate. Its gravity was strong enough to pull together the galaxies and clusters we see today, giving the cosmos its rich structure, but it was not strong enough to save it from this ultimate frozen silence. By mapping the invisible, we are not just uncovering the past, we are reading a prophecy. The ghostly presence of dark matter holds the key to the long-term future of every galaxy, every star, and every atom. This quiet revolution in mapping the invisible is about to become a deafening roar. Perched atop a mountain in Chile, the Vera Sea, Rubin Observatory is preparing to open its eye to the cosmos, launching a mission that will transform a decade of patient watching into the most ambitious movie of the universe ever made. Its heart is a colossal digital camera, a technological marvel with a resolution of 3.2 gigapixels. To grasp that scale, you would need over 1,500 high-definition television screens just to display a single, full-resolution image from this instrument. Every few nights for 10 years, this camera will capture an enormous, ultra-deep photograph of the sky, not just once, but over and over again. This relentless project is called the Legacy Survey of Space and Time, and its purpose is to record the cosmos in motion. It will detect and track billions of galaxies, watching for the subtlest changes in their light and position. For the hunt for dark matter, this moving picture is the ultimate tool. By applying the principles of weak gravitational lensing to this unimaginably vast dataset, astronomers will not create a single snapshot of the cosmic web. They will chart its evolution. They will watch how the dark matter filaments thicken and how the halos around galaxies grow over cosmic time, creating a time-lapse map of the invisible universe's very life cycle. This dynamic view will allow for precision tests of the dark energy that drives the expansion, measuring its push with a finer ruler than ever before. But perhaps the most thrilling possibility lies in the details of the map itself. The prevailing cold dark matter model assumes these particles are essentially loners, ghostly entities that pass through each other without a second glance. The LSSD map will be so exquisitely detailed that it might detect a slight stickiness in the dark matter, a faint suggestion that these particles do interact with each other in some minuscule way beyond gravity. Such a discovery would shatter the simplest models and open a window into the hidden physics of the dark sector itself. This is not merely another telescope, it is the next great leap in cosmic cartography, a machine designed to write the definitive atlas of the real universe, the one we have never been able to see. While we chart the skies from mountaintops, a silent sentinel now orbits 1 million miles from Earth, built for a single, profound purpose. The European Space Agency's Euclid Space Telescope is not just another observatory, it is a machine engineered to see the invisible. From its vantage point in the deep quiet of space, free from the shimmering distortions of our atmosphere, Euclid is embarking on a 6-year mission to map the geometry of the dark universe. Its power lies in a uniquely wide field of view, allowing it to capture vast swaths of the cosmos in a single glance. like a cartographer sketching continents instead of individual streets. This grand survey will meticulously measure the shapes and precise positions of over 1 billion galaxies, but it will do more than just count them. By analyzing the redshift of each galaxy, the way its light is stretched to longer, redder wavelengths by the expansion of the universe, Euclid can pinpoint its distance. This transforms a flat picture into a three-dimensional atlas, a cosmic globe charting the universe's large-scale structure across an incredible 10 billion years of cosmic history. This depth is the key to everything. By looking so far back in time, Euclid will not just map where the dark matter is today, it will watch how its cosmic web has grown and evolved. It will trace the thickening of dark matter filaments and the swelling of halos, creating a time-lapse film of the invisible skeleton's assembly. This historical record is precisely what we need to decode the push and pull between dark matter and dark energy. How has the relentless force of dark energy altered the growth of these structures over the eons? Euclid's immense, space-based catalog will provide a complementary dataset to ground-based surveys like the one at the Vera Sea. Rubin Observatory. While Rubin will create a brilliant, high-resolution movie from Earth, Euclid provides the stable, deep space perspective, its vision unblurred, its measurements exquisitely precise. Together, these two giants of modern astronomy will cross-check and reinforce each other, weaving a single, definitive narrative of a universe shaped by forces we are only just beginning to perceive. Far above Earth's atmosphere, a golden eye is looking back in time. The James Webb Space Telescope was not designed to hunt for dark matter directly, yet it is revolutionizing our search by witnessing the universe's first dawn. Its mission is to capture the faint, redshifted glow of the very first stars and galaxies, emerging from the cosmic dark ages. This is a journey to the era when the primordial cosmic web was still tightening its grip, and dark matter halos were just beginning to pull the universe into structure. By observing these infant galaxies, we are not just looking at ancient light, we are studying the original blueprints of cosmic architecture, seeing how dark matter's invisible scaffolding dictated where the first lights would switch on. The data is already presenting puzzles. Some of these early galaxies appear too massive, too bright, and too mature for their age. They seem to have formed far more quickly than our best simulations predicted. This does not necessarily mean dark matter is wrong, but it might mean our understanding of how ordinary matter condensed within those early dark matter halos is incomplete. Were the first stars somehow more efficient at forming? Did supermassive black holes emerge earlier and influence their growth? Or does this hint at something more fundamental about the nature of the dark matter particle itself, perhaps influencing how smoothly it clumped in the early universe? Every galaxy JWST discovers in the cosmic infancy is a data point, a crucial test for our virtual universes. We can now ask a profound question. Do the galaxies we see at the edge of time match the ones our supercomputers grow in their dark matter nurseries? The answer is refining the conversation between the dark and the light, forcing our models to become more sophisticated, more alive to the intricate dance that built everything we see. JWST provides the ultimate reality check, a glimpse of the universe's first structures being born within the embrace of the invisible. The grand cosmic web is not a smooth structure. Within every vast dark matter halo, supercomputer simulations predict a hidden metropolis of smaller structures. These are subhalos, countless clumps of dark matter that should orbit within the larger halo like moons around a planet or bees swarming within a hive. According to our most trusted models of cold dark matter, the Milky Way's immense halo should be teeming with thousands of these smaller satellites. But when we look up at the sky with our most powerful telescopes, we only see a few dozen small galaxies orbiting our own. This glaring mismatch is known as the missing satellites problem, and it presents a fundamental puzzle. Where are all the rest? One compelling possibility is that most of these subhalos are completely dark. They are pure, unadorned clumps of dark matter, lacking the dense gas required to ever ignite a single star. They possess the gravitational mass to be considered small galaxies, but they remain eternally invisible, their presence only detectable through their subtle gravitational influence. Another explanation could lie in the physics of star formation itself. Perhaps when the universe was young, the intense radiation from the first stars and galaxies heated the cosmic gas, preventing it from cooling and collapsing inside the very smallest dark matter halos. In this scenario, the subhalos exist, but they were stillborn, starved of the material needed to shine. Resolving this mystery is like trying to find invisible islands in a dark ocean by the waves they push aside. Astronomers are hunting for the faintest, most diffuse dwarf galaxies, the ones that may have managed to form only a handful of stars. Others are searching for the telltale flickering of distant stars, their light momentarily magnified if an invisible, compact dark matter clump passes in front of them. This search probes the smallest scales of the dark universe, testing the very nature of the dark matter particle. Does it have a tiny bit of internal motion that would prevent it from clumping on such small scales? The missing satellites are not a failure of our theory, but a guidepost. They are forcing us to look deeper into the complex dialogue between the dark universe and the birth of light, challenging us to understand the very first moments of cosmic structure on the smallest of scales. Perhaps dark matter is not the ultimate loner we have always imagined. What if, on the rarest of occasions, these ghostly particles could actually bump into one another? This idea, known as self-interacting dark matter, offers an elegant fix to some of the most stubborn puzzles on the smallest cosmic scales. The standard model treats dark matter as cold and completely collisionless, silent ships passing in the night, governed only by gravity. This works beautifully for the large-scale cosmic web, but it predicts that the centers of galaxy halos should become incredibly dense, peaked cusps of dark matter. Observations of many dwarf galaxies, however, suggest their dark matter cores are shallower and more smoothed out, like a soft, rounded hill instead of a sharp mountain peak. How could this happen? If dark matter particles have a very small but real chance of interacting, of bouncing off each other, they would naturally redistribute their energy. Just as a crowded room of people jostling will eventually spread out evenly, these occasional collisions would transfer heat from the dense, hot center of a halo to its cooler outer edges, gently eroding that central cusp into a smoother core. This subtle social life would also influence the population of subhalos. The relentless gravitational tug of war within a large galaxy like our Milky Way can tear smaller clumps apart. If those clumps are made of self-interacting dark matter, the particles within them would collide and lose energy, making the subhalos more vulnerable to being shredded and dissolved. This could naturally explain why we see fewer small satellite galaxies than the simplest simulations predict. The missing satellites might not be missing at all, but simply dark, dissolved clumps whose particles were too sociable for their own good. This is not a wholesale rejection of the cold dark matter model, but a sophisticated refinement of it. We are now searching for the fingerprints of these interactions in the detailed shapes of galaxy clusters and the delicate dynamics of the faintest dwarf galaxies. By comparing the sky to ever more detailed simulations, we are asking a profound new question about the invisible majority of our universe. Does it simply exist, or does it, in its own silent and invisible way, also communicate? Another dark horse candidate emerges from the universe's violent birth, Before the first stars ever ignited, in the searing heat of the first second, the cosmos might have forged black holes. These are not the stellar mass black holes born from dying stars, but primordial black holes, PBHS, created by the overwhelming pressure of density fluctuations in that infant universe. Imagine the fabric of spacetime itself pinching off into tiny, incredibly dense knots. If these exotic objects formed in abundance, they would be the perfect ghost. Completely dark, possessing tremendous mass and scattered everywhere, they could, in theory, be the dark matter we have been seeking. Their sheer gravity would explain the rotation of galaxies and the lensing of light, all while remaining utterly invisible. Yet the universe has ways of constraining even its most dramatic possibilities. Scientists have searched for these phantom black holes by watching for a specific kind of event. If a PBH drifted in front of a distant star, its gravity would act as a tiny lens, briefly focusing the star's light and causing it to flare in brightness for a few minutes or days. This is microlensing. Massive, dedicated surveys have scanned millions of stars for years looking for these characteristic flickers. The result has been a profound silence. There simply are not enough of these microlensing events to account for all the dark matter as black holes of a certain size. The cosmic microwave background adds another constraint. If a significant population of PBHS existed in the early universe, they would have been voracious feeders, gobbling up matter and emitting radiation as they ate. This process would have injected extra energy into the primordial plasma, leaving a distinct imprint on the CMB's temperature patterns that we simply do not see. The data has systematically closed the door on black holes across a wide range of masses, from the size of planets to hundreds of solar masses, as the primary component of dark matter. One narrow window remains tantalizingly open, the realm of the incredibly small. A vast population of asteroid-mass primordial black holes, each no heavier than a large mountain, could potentially still be hiding in the shadows. Their tiny individual mass would make them difficult to detect through microlensing, and they would have evaporated less energy in the early cosmos. While they cannot be the whole story, this sliver of possibility is a powerful reminder. The ultimate answer to the dark matter mystery might not be a new particle from a lab, but a relic from the most exotic physics of the first instant, a fossil from the moment of creation itself. Our own particle physics has already introduced us to a true ghost. The neutrino is a subatomic whisper, a particle so aloof that trillions pass through your fingertip every second without a single interaction. It is abundant, produced in the hearts of stars and in the violent deaths of supernova, and for a moment it seemed a perfect candidate for the cosmic missing mass. But the neutrino possesses a fatal flaw for this role. It is simply too fast. Born in high-energy processes, these particles fly at velocities incredibly close to the speed of light. This incredible speed defines them as what cosmologists call hot dark matter. To understand why this is a problem, you have to return to those supercomputer simulations of the early universe. When scientists program a cosmos dominated by such fast-moving particles, the results are a cosmic disaster. The relentless, high-speed motion of hot dark matter acts like a cosmic smoothing iron. It washes out the very gravitational seeds that are meant to grow into galaxies and clusters. The tiny ripples in the primordial plasma are erased before they can collapse, preventing the formation of the smaller, intricate structures we see woven throughout the cosmos today. A universe built on hot dark matter would be a far more barren and empty place, lacking the rich tapestry of dwarf galaxies and the finely detailed cosmic web we observe. Neutrinos do indeed contribute a minute sliver to the dark matter budget, a faint, hot component in a much colder sea. but the overwhelming majority of the invisible mass must be cold, moving at speeds far slower than light. This critical distinction between hot and cold is not just academic. It is the fundamental reason our universe looks the way it does. The slow, patient pull of cold dark matter allowed gravity to work its magic over billions of years, gently gathering matter into the first stars and the magnificent galaxies we see glittering in the night. The silent, swift neutrino is a ghost we can detect, but it is not the primary architect of our cosmic home. This fine-tuning extends to the ghostly presence shaping our cosmos. The very existence of life may be tethered to the precise amount of dark matter that flooded the early universe. This idea is known as the Anthropic Principle, a profound and somewhat haunting suggestion that the fundamental constants of our reality are not random, but appear carefully balanced to allow for observers like us to emerge. Consider the cosmic consequences if that balance were upset. If dark matter were significantly more abundant, its immense gravitational pull would have accelerated the collapse of the primordial gas. Galaxies would have formed too quickly and too densely, leading to a chaotic universe where stars are packed dangerously close, with planetary systems likely torn apart by violent gravitational encounters. There would be no stable, quiet orbits around a star like our Sun, no peaceful billions of years for life to slowly evolve. On the other hand, if dark matter were far more scarce, the opposite disaster would unfold. The gravitational glue would have been too weak. The initial ripples in the cosmic fabric might never have gathered enough pull to form galaxies at all. The universe would have remained a vast, dark, and ever-expanding sea of isolated hydrogen and helium, a cosmic stillbirth where no star ever ignited. Our solar system, our planet, and every living thing on it are here because the density of dark matter fell within a remarkably narrow, life-permitting window. It provided just enough gravitational scaffolding to build galaxies at the right pace, and within those galaxies, to create quiet suburban neighborhoods where stars could host stable planetary systems. This perspective connects the most microscopic search for a phantom particle to the grandest of questions. The hunt for dark matter is not just about mapping the invisible. It is about understanding why a universe with such specific, ghostly properties came to be, and why we are here to wonder about it at all. The hunt for an invisible cosmic substance has quietly revolutionized our own world. To listen for a ghost, we first had to learn how to build a room of perfect silence, and that engineering challenge has spun off technologies that now touch our daily lives. Consider the heart of a dark matter detector, a vat of liquid xenon chilled to -100 degrees Celsius. The quest for absolute purity demanded breakthroughs in material science, learning how to refine elements to a level never before achieved, stripping away even the faintest traces of naturally occurring radioactive contaminants. This mastery over ultra-pure materials is not just for physics, it directly enhances the sensitivity of medical imaging. The detectors in positron emission tomography, or PET, scanners, used to spot cancers and map brain function, now benefit from these exquisitely clean crystals and gases, providing doctors with a clearer, sharper view inside the human body. The same photomultiplier tubes that wait to catch a single photon from a WIMP collision are now being adapted to create new, highly sensitive cameras that can see the faint glow of biological processes at the cellular level. This is the hidden dividend of pure curiosity, the pursuit of a fundamental question forcing us to become better craftsmen of reality. The need to process the unimaginably vast datasets from sky surveys and supercomputer simulations has driven the creation of sophisticated new algorithms for finding subtle patterns in overwhelming noise. These data mining techniques are now being applied to national security, helping analysts sift through immense streams of information to identify true threats, and in finance to detect complex, fraudulent activities hidden in global markets. Even the deep underground laboratories themselves, carved out of solid rock to shield against cosmic rays, have become unique testbeds. Their profound silence is ideal for developing the next generation of quantum computers, where the slightest environmental interference can destroy the fragile quantum states necessary for calculation. The machines we built to map the invisible universe are in turn helping us build a better, smarter, and healthier visible one. This relentless drive to perceive the imperceptible has not yet found its primary target, but it has already expanded the horizon of human capability, proving that the journey to answer a cosmic question can reshape our own world in the most practical and profound ways. The search for the invisible universe is no longer confined to professional astronomers. One of the most powerful tools in mapping dark matter has been the collective curiosity of millions of people around the world. Projects like Galaxy Zoo open the cosmic vault to everyone, inviting the public to do something computers still struggle with, simply looking at galaxies and classifying their shapes. Each spiral, each elliptical, each strange cosmic merger identified by a volunteer becomes a vital data point. This is not a game, it is real science. These classifications form the foundation for weak lensing studies, where knowing a galaxy's true, undistorted shape is essential for measuring how its light has been warped by intervening dark matter. This crowdsourcing approach has proven astonishingly effective, processing immense datasets in months that would have taken a small research team decades. But the impact runs far deeper than speed. By participating, people forge a personal connection to the cosmos. They are no longer passive observers but active contributors, their clicks helping to trace the contours of the cosmic web. Understanding dark matter is not a niche pursuit for experts in ivory towers. It is a fundamental human endeavor to comprehend our own origins and place in the universe. Every galaxy classified is a vote for curiosity, a shared step in a grand collective project to illuminate the darkness. This engagement builds a vital legacy of public support and wonder, ensuring that the quest to map the invisible remains a journey we all take together. The hunt for the invisible is accelerating into a new era of unprecedented scale. Next-generation detectors are moving beyond the current vats of xenon, planning for multi-ton instruments that will be 1,000 times more sensitive than those operating today. These colossal observatories will be buried even deeper, in even quieter environments, listening for a whisper that has so far remained just beyond our hearing. If a WIMP exists within the vast range of masses we have yet to rule out, these behemoths are designed to finally hear its gentle tap. At the same time, we are rebuilding the Big Bang on Earth with even more powerful machines. Proposals like the Future Circular Collider envision a new ring tunneling under the European countryside, with a circumference over 10 times longer than the Large Hadron Collider. This incredible instrument would smash particles together with such ferocious energy that it could literally create dark matter particles in its detectors, studying them not through their absence but through their birth. This multi-pronged assault extends far beyond our planet. In space, missions like the Nancy Grace Roman Space Telescope will join Euclid in creating staggeringly detailed three-dimensional maps of the cosmic web, while from the ground, the Vera Rubin Observatories' decade-long movie of the sky will capture the subtle evolution of dark matter's structure. This is no longer a series of separate experiments. It is a single, coordinated campaign, a symphony of astrophysical observation, deep underground detection, and high-energy collider physics, all conducted on a global scale. The solution may not come from where we expect. It might emerge from a tiny anomaly in the data of a space telescope, a faint signal in a crystal detector that no one predicted, or a mathematical breakthrough that reveals not just a new particle, but an entirely new force or even a hidden dimension. The next decade promises to be the most transformative period in this century-long quest. We are no longer just searching for a missing component. We are probing the fundamental architecture of reality, and the invisible universe is finally being cornered. Our journey through the invisible universe reveals a cosmos where the real story is told not by the glittering stars, but by the profound silence between them. We are surrounded by a ghostly architecture, a substance we cannot touch or see, yet its gravitational signature is etched into the very fabric of reality. The evidence for this dark matter is no longer a single clue but a symphony of proof, from the impossible speed of orbiting stars to the warped light of distant galaxies. It is the hidden hand that spun the first galaxies into being, and now weaves the vast cosmic web that spans the void, while the fundamental particle at its heart remains one of science's most profound mysteries. Our relentless efforts to map its structure are bringing us closer than ever to a revelation. We have drawn the blueprints of the invisible, learning to see not with our eyes, but with our minds and our most powerful machines. The greatest discoveries in human history have always been like this, lying not in what we can plainly observe, but in what we have the courage and creativity to imagine. We stand at the edge of this magnificent frontier, ready for the next great leap. What do you think this invisible universe will ultimately reveal about our place in the cosmos? Share your thoughts in the comments and subscribe for more journeys to the frontiers of knowledge.